Hello, my name's Michael Avery. I work for Cadence Design Systems. In this video, what I'll be doing is showing how we can associate various assertions in different languages with some DUTs, some just design modules, which are also in different languages. So when we've got the requirement that we have to write assertions about how a design behaves, then we're not always kind of have a free hand in which language we use. For various reasons, we might work for a company who's required another company who uses a different assertion language, for example. So you might be using PSL, but the company you just acquired uses SVA. You might have third-party providers and so on. So what we're doing in this example is we've got a mixed language hierarchy, and we're going to apply both SVA and PSL to various places in that hierarchy. So one thing people commonly want to know how to do is how do I apply system Verilog assertions to a VHDL module that's embedded under a Verilog top, for example. So this is a design that's already loaded, and what we can see here is top is a Verilog module. Okay, so if I just click the right button and say send to source browser, we'll have a look at what's in there. Okay, so what's in there is a top level module with no ports. We've got some signal declarations, and we've got some instantiations here. So we're instantiating a unit with this name, my VHDL DUT. There's two instances with the instance names VHDL1, VHDL2. This is what we see here and what we see here. So these are identical modules that have been instanced. And likewise for this, we've got some Verilog DUTs, which is the instance name is Verilog 1 and Verilog 2, and we've got the port mapping to them here. And all this top module is doing is applying some really simple stimulus via some tick include file. Okay, so let's go and have a look at the Verilog, for example. So in the Verilog, I can see here in this design browser I have a number of signals in here and also a number of properties I can see. So this kind of icon here tells me that's a property. Okay, so let's say I want to go and have a look in here. I say send to source browser. Okay. And in the source browser, we see our Verilog code with ports, input and output ports, and some always blocks which have labels. So this one has label P0, P1. And if we're to expand this, we will see those processors there. And we will also see the signals that are declared via ports or internal signals. Okay, now just for reference here, the actual functionality of the VHDL design is identical to the Verilog design. So this is the Verilog design module we're looking at here. And the VHDL module contains exactly the same functionality. So as well as having normal RTL looking code in here, we also have some system Verilog assertions. So here we have a declaration of a property. And here on this line 31, we instance that property, and the instance name is SVA in Verilog DUT, as we can see there. Okay, so that's the name of that property instance there. Okay. We can also see we've got some PSL properties. So in the same module here, we're including some PSL properties by a mechanism that uses comments. So what this does, and all vendors do this, from the early days of PSL before system Verilog assertions existed, this is all you could do if you wanted to include assertions in your design modules. You put a comment characters and then PSL, so this pattern here, what that indicates to the tool compiling this is what follows it is a PSL statement. Okay, so there's our property declaration there in PSL, and here's the instance here. So the name of the instance, PSL in Verilog DUT, is what we see there highlighted. Notice how these windows are interlinked with the highlighting. So what we've got in this Verilog DUT we're looking at, we've got one instance of an SVA property, one instance of a PSL property, and they're both actually checking identical things. So just as a kind of FYI here, all of these examples we're seeing are declaring exactly the same properties. It's just if we have a signal called A followed by B, it implies that the next cycle we have C followed by D. So all of these signals are interconnected electrically, so they should all pass and fail at the same time, which will become clearer as we go on through the description. So what we've got then, just to summarise where we're at the minute, we've got a Verilog top level called top. We have two instances of a Verilog DUT called Vlog1, Vlog2, each of which contain processors and contain some embedded code, which is SVA properties and PSL properties. Let's look at the VHDL DUT now. So we'll just click on one of the two instances, click the right button, say send to source browser, and here's the code for that. And again, this is identical in function to the Verilog DUT. So we have some ports, some signal names. We have processors. If I expand the design browser here, you can see the processors P0, P1, P2, which have the same functionality as the Verilog equivalent. And here we have, using the commenting kind of scheme we described earlier, a PSL property. And here's the instance of it on line 50. So let me click that, it will highlight it over there. Now in PSL, this is the mechanism that was used from the early days. What came on along at a later point in VHDL 2008 VHDL Language Reference Manual was the ability to put PSL code natively inside of VHDL. So whereas here we've got a property declaration on lines 48-49 and we have the instantiation on line 50, we can write this directly in code, so it's not a comment anymore. Okay. Now, one thing to be aware of, which is why I mentioned this, is you can't just simply delete these comment characters here. Okay, so you can't delete the comment characters from the beginnings of line 48, 49 and 50 and hope it works, because it doesn't. What you have to do is put the property declaration in a declarative region, for example in here, in the architecture declarative region. Okay, that's where you're expecting to see things declared, like signals, for example. And when you instance it, it's a concurrent statement. So notice here, this is the instance of that property that was described above, and there is no comment characters here. So again, we can see these are our two properties that we've got here. There's not going to be any SVA in here because you're not allowed to put SVA code natively inside of VHDL. So a question to ask ourselves at this point, now we've seen the DUTs, is why did we bother putting these properties inside along with the RTL code? And there's no right or wrong answer on this. It all depends on what you want to achieve. An advantage of putting it directly in your RTL code is that it can never get separated. So it's not like you can describe the properties in a separate file and somehow hope that you don't lose that separate file containing your properties. You may not want the property and the RTL to get separated. So if that's your situation, then that's what you would do. If you're going to do that, however, what you have to be careful of is that you hide these properties from other tools, like, for example, synthesis, equivalence checkers, because it may cause them to fall over. So you might want to surround these with kind of a synthesis pragmas or generate statements if it's VHDL, or if-defs if it's Verilog, in order that the tool doesn't need to parse it or can be forced not to parse it. So again, the question of whether you put your properties directly in your RTL or not is a question of personal preference. Most people, in my experience, choose to put the properties in a separate file and associate with them later on, because this is less reusable. If it's in the RTL here, it's always in the RTL. You can't get rid of it. You may also have your hand forced by the fact that this code is, this VHDL code in this example, might be a legacy code that cannot be checked out of source control, so you don't have write access to it. So there's no way you can go and then apply properties to it or change the behavior of properties. You would need write access. So given all those factors, as I previously stated, then most people define their properties in external files somehow. And what we'll do next is show how can we do that. So to recap where we were, we've got a Verilog top module here. And inside of there we have two instances of the same VHDL module, two instances of the same Verilog module. And inside all of those, each of them had one PSL property, and in the case of the Verilog ones, they also had an SVA property. As well, in the VHDL, we had direct native PSL, so effectively it gave us a total of two PSL properties. But if we now look at this, we can see, if we click on this one, for example, we can see we've got a whole new set of properties from somewhere. Where do they come from? And likewise for the Verilog. We can also see, for example, in the VHDL, we have a signal now called my VUnit VHDL signal. In the Verilog, we have something called my Verilog VUnit reg. Okay, so let's have a look in the code and see if anything's materially changed. So let's send this to the source browser, the VHDL. So PSL in VHDL VUnit is the name of a property. If I look inside of here, I won't find anything with that name. Okay, I'll just up the properties I had initially. If I look for this my VUnit VHDL signal, where's that? This is the declarative region where it could be. This is the port list, it's not in there. So these have come from somewhere else, we might conclude. Furthermore, if we expand this, we can also see that in the VHDL we have another instance of something called this is the name of the instance name here. And if we look in the Verilog, we also have something of the same instance name. Where did that come from? Let's have a look at in the source browser. Okay, and what we see here is it's another module with inputs only. This is known as a verification component. So basically this is just a module whose purpose is for verification. So inside of here we can have things like properties, we can have cover groups, we can define normal HDL looking code. But the question is then, how do these things get there? Because we haven't changed the DUT source code in any way. How do they get there? So there's two things going off here. We've applied a PSL verification unit to these modules, to the DUT modules, and we've also applied a system Verilog verification component to these using a construct called bind. Okay, so let's see how we did that then. For system Verilog, if we go to the top, what I've done in this particular case is added some statements called bind statements. Okay, so these were previously commented out on the example I showed before. And the way in which these bind statements work are like this. I say bind to, and then I give a name of a design module. This is the name of the verification module I wish to bind to it. So what I'm effectively doing is I'm creating an instance of what's highlighted inside of a existing HDL DUT, and the instance name will be the name. So that's where that name came from. Okay, so I'm binding to the VHDL on the module. So that's where that module came from. Okay. So let's go and look at this code to see where that's described. This is the name, SVV comp is its name, and what we did is create an instance inside of the VHDL with that instance name shown, and inside of that all this stuff is contained. So this is a way of applying system Verilog assertions. So notice down here we've got some instance of a system Verilog assertion applied. Because this is just there's nothing different about this than any other standard system Verilog module. We can also put PSL as well if we wished. So we're actually applying an embedded comment PSL inside of this as well. So if I click on this, we'll see in here, this is where our properties are coming from. These names correspond there to that. If I'll highlight this one to that. Okay, so we've attached system Verilog assertions to VHDL underneath the Verilog top. So obviously there's many permutations of this, and the intention of this video is trying to show you enough information to work out for yourself what to do for your particular unique situation. So what I've also got, if I were to go to either of the Verilog, notice as well what we'll show is that this myBind inst name appears for every instance there is of a module. Let's go to the top again. So what the bind statement says is every instance I have with that name, that's the name of the VHDL module, my VHDL DUT. Okay, so let's look at that. That's where that name's coming from, the name of the entity. So what this is saying is for every instance I have, and there could be 1,000 of them, there could be one, There could be 100, who knows. In this case we've only got 2. Create an instance of this with a name as shown. Okay, so that's where these ones come from. Notice there's another bind statement here which is binding to a design unit whose name is this, my Verilog DUT. So where does that name come from? It's the name of the Verilog module, my Verilog DUT. Bind to that, an SV comp, that's the same assertion module we've seen before, give that its instance name. So this instance name doesn't need to be the same as the one on the line above, it could be different. Okay. So that's how these instances get there, via simply that bind statement. That's the only things that would be required in order for that to happen. Okay, so what else have we done? Well, we've also got a VUnit attached here. So we can see when we look here, we've got some more PSL properties that we didn't have before, and we noticed that in the VHDL DUT we didn't add any more properties. So where have they come from? They've come from something called a verification unit. So a verification unit in PSL is just an external text file that contains a container, and inside of that container is a bunch of verification code. So let's take a look inside of the VHDL here. We can see we've got some properties down here that we know are not in the HDL for that VHDL module. So let's take this one here. Where did that came from? So let's click the right button, say center source browser, and there we can see that it's showing us a file with this name here. Notice the extension .psl. This is what's called a VUnit. Okay, so the way in which we describe this is the keyword VUnit there. We then give a name for that container. So remember, we're describing a container that has verification code in it, and we're associating that with this name, my VHDL DUT. That is the name of our entity. Okay. So if we were to look at this, let's just look at the source code for this. That's the name of our entity here, my VHDL DUT. So because we've got so many properties to look at, let's have a look at another thing, another window we may not have seen before. So if I go Windows New Assertion Browser, it will show me all of the assertions I have throughout my whole environment, and I can filter that in whichever way I wish. So I can filter it on instance name, for example, as well as all the others, and I'm only seeing now things that are applicable to that, that contain that pattern in the instance name. So let's get our another way of getting our PSL back again. Let's just say center source browser for this. So notice in here what we've got, and if I get the design browser visible while we're looking at this, inside of the VUnit, this just looks like VHDL code here. I've got a signal declaration here. So if I click on that, notice that's where that signal came from. I've got a process here. So if I click on that, I can see in my VHDL1 instance I have this process, and I've got a PSL property as well here. So if I click on that, I can see it in here. So that's where they came from. So the VUnit allows us essentially to it's as if we're taking this code and pasting it inside of the RTL that we may not have write access to. Okay, so it's a mechanism for doing that. So we can put any code we like inside of here. So that's where those properties came from. Now in the Verilog one, so if we look at one of the Verilog instances, let's choose on this, for example. Where did that property come from? So that's the source browser. That's coming from a VUnit as well, and we can see the name in the title bar of this window of the file. It's a .psl file. Again, keyword VUnit, that's the name of the container. We're applying it to a module with that name. That's the name of our Verilog DUT module. Inside there we're describing a reg, so that's where that reg came from. We've got an initial block, we've got an always block, we've got a property written in PSL, okay, and we're asserting it there. And because it's just, you know, a container that we can put code in, and effectively it gives us the capability to paste that code inside of the Verilog module, HDL module the DUT, which we may not have write access to. Otherwise, we can also put SVA in there. So we're using PSL here, a PSL V unit, to apply SVA to Verilog, which we may ask, why do we do that? It's just showing you all the different mechanisms in which you can apply assertions to designs in various different languages. Okay, so that's again. So the next question then is, how do these V units get associated with the actual write file? Well, we've got the name of the module there, but we also have to do something extra. And that's something extra we have to do is a switch. Okay, so if we look at the script that actually ran this. Okay, so the switches we're using here are -assert. So what that does is enable any kind of PSL statement that's inside of a DUT, or rather the file that you supply here, to be parsed. If you don't have -assert, it won't be, it'll be ignored. So that's the code that's actually embedded in your RTL code in your DUT itself. If you want to apply a V unit to a particular file, we use one of these switches here, -prop file. So the -prop file VHDL says the V unit I'm going to apply to this is going to contain VHDL syntax. Okay, so in PSL you can use either VHDL or system Verilog. The other switch that says -prop file vlog, it means the PSL V unit file, this file with extension .psl contains Verilog syntax. So -prop file vlog. And there we just give the name of the file itself. So what we're doing is we're attaching that file containing the V unit to the design when we're compiling it. So you notice all these -run compile is doing compilation only. So just to recap on that, -sv is needed to enable system Verilog keywords, like for example SVA assertions. -prop file is needed to apply a V unit to a file. So the name we give after the -prop file is the name of a file with extension .psl, and that V unit contains either VHDL syntax internally or contains Verilog syntax internally. And by the way, there's nothing stopping us applying a V unit containing Verilog code to a VHDL module if we wished. Okay, so let's take the scenario we already have with the VHDL and Verilog instances that have V units attached to them and also have a verification component attached to them via a bind statement, and take that a step further just as an example of what we could do. Okay, so what we've got is another verification component here. So that's its name. So verification components are just normal Verilog modules with inputs only, okay, because they're there just for verification. And inside of there I'm declaring some other HDL signal. I could have another process component instances if I wished. And I'm also adding another SVA property. However, I don't wish to bind this to every single Verilog module or bind this to every single VHDL module. I want to pick and choose where I apply this to, because this only has a very specific purpose, let's say on one instance out of 10. So how would I do that? Let's go back to my place I did my binding. So you might recall from earlier that we did this. We bound to any instance of this VHDL entity a particular verification component. So what we're doing here, we want to bind to specific instances. So it's the same kind of syntax, bind, but this time what we're supplying is the name of a specific instance to which we wish to bind this verification component that we were just looking at in the source browser. And the name of the instance will be that. Okay, and there's the signal binding. Likewise, this one's bound to a specific VHDL instance. This is bound to a specific Verilog instance, so top.vlog2 is the instance name I wish to bind this to. I'm binding a verification component with that instance name. Okay, and I'm making my binding. So that's the differences. Now in my run script, what I have to make sure also is that I compile that vcomp I just saw. Okay, so another underscore vcomp was this file we were looking at a moment ago, and I've run this. Let's go and see how this affects what I see in the tool. Here we've got, let's filter on, go to our binding actually. Let's filter on this instance name here, vlog2. and have a look what do we have in here. So notice this is that SVA assertion. If I send that to the source browser, this was this verification component, this additional one we've just written. Okay, and how that's applied. How the waveforms are plotted as well here, actually, if you want to plot things as waveforms, what's often useful, if you click the right button and go create probe on whichever assertions or group of assertions, the default is state probe, which just shows you if it's pass or failing. If you select transactions, it will plot them as transactions, meaning it will show you the time during which the assertion was evaluated, and you can also punch in this button to show any signals the assertion references. And what you end up with is something that looks like this, you know, with the start finish time for an evaluation of assertion, and finish means it passed, failed means it didn't pass, it failed. So these things are plotted as assertions. And notice, because all these properties are the same, they're describing the same thing on the signals which are electrically connected, they'll all pass and fail at the same time. So that's how that was achieved. So anyway, we're back at the point now. What we need to check is, because what we hoped happened is we did instance-based binding. So let's go and look. Yeah. If I expand out this VHDL, I can see this previous vcomp that I attached to every instance of VHDL design unit. Okay. So my bind instance name appears in both of them, but this one here, that only appears in the instance with the name VHDL1, top.vhdl1. Okay, so it only exists for that one. Likewise, if we expand the Verilog one, we will notice that this instance only appears for instance name vlog2. Okay, now I might be looking at this and thinking that's all very well, but you know what, I don't want to have to go and keep editing my top file. You know, this may be checked in on the source control. I don't want to have to keep modifying this to decide what I bind to. So what I'd really like to do is not do this binding in that place there in top. I want to do it somewhere else. Okay, so what we'll do then is we'll comment out these two things. So those bind statements don't apply, and we're going to do them elsewhere. In fact, there's two places we can do them elsewhere. One of the ways in which we can do this is that bind statement. We can move it to a we can move it into another file. So what we can do is we've got a separate file here, and we're going to. Our intention is to elaborate this as a separate top. So the bind statement doesn't have to exist anywhere in particular. We can put it anywhere we like. So what we can do is move these bind statements. So what we're essentially doing is we're copying and pasting them from that top.v file here, top.sv file. We're copying and pasting these ones here that we commented out there and there, and we're putting them in a separate file that we showed here. Okay, so we just moved them somewhere different, so we didn't have to keep editing top. So one of the things we can do is we can do this. Just add to our irun command. So we're compiling all these same modules as we were earlier, and when we do the final invocation of the simulator, we just add that because it's just a system Verilog file as a system Verilog file, and the binding will go and take place as we wished. Okay, so that instance-based binding we've placed in that other file. Another way in which we can do this is via an external switch called xbind. Okay, but what we'll do for the time being is just show you what happens when we've run this. And this is what happens here. We've got our top that we're familiar with now, and let's open some of these instances to which we bound instance specific vcomps. So that was one there. Notice we didn't find the corresponding thing inside of VHDL2 because we didn't have that in our instance specific bind. In Vlog2 we had this instance specific vcomp, and Vlog1 we didn't. Okay, so where did these bind statements come from? As we saw, this place here. Okay, so that's the file name that I added to the irun command, and all it was, as shown down here, is what I wrote, exactly what I wrote. So that's where the bind statements are coming from to put these instance specific things inside of there. I've had to go and write that myself, of course. And just as a recap, how I got that to actually all happen was just simply to add this to my irun command. Okay. remember that I commented out in top those bind statements that were there originally. So if I were to go to top, those bind statements are the ones commented out there and there. Let's look at an alternative to what we've just done. I've done another run now, but this time, rather than having that top elaborating a separate top level module as I did before, I have this thing here that the tools put there automatically. So let's look what's in that. In there is exactly the same bind statements I had before, but not directly. It's done by including some file here called standalone bind statements.txt. So what we've done in this case is we've achieved the same effect we had previously, namely we've added that extra vcomp, but we've done it via a irun switch instead. Okay, so let's look at the run script which did this. The run script that did this is here, and notice the difference is we've added, instead of having, as we did before, that system Verilog file, which of course requires compiling, we've done this instead. We've said -xbind and we've provided the name of a text file. Okay, that text file contains only the bind statements and the rest gets wrapped for us as we saw in the source browser there. Okay, so just to show you here, this is just a copy and paste of the bind statements. So all that's in here is bind statements. The tool goes and wraps this up in a separate top for me, and I supply it as a -xbind switch so I don't have to compile and recompile. So basically it gives you more flexibility on how you create your scripts and how you invoke your runs. Okay, so hopefully you find that video useful. We've just done just about everything that's possible. We've applied SVA to both Verilog, which we knew we could do already, and VHDL. We've done it in the RTL file itself and outside of the RTL file. We've managed to bind assertion modules only to instances we wanted to, and we've also done it globally, meaning we can bind an assertion module to every instance there is of a corresponding DUT module. And we've applied PSL to system Verilog, and we've applied PSL to VHDL. And we've also applied via a PSLV unit some SVA code, so we've kind of gone in circles back on ourselves. So the purpose of this was not to suggest that it would be a good idea to start applying all different assertions in different languages using a variety of methods. It just gives you a kind of a idea of what's possible, so that when you're pushed in a corner by circumstances like you've had IP from a third party or another part of your company that uses different languages from you, or from an acquisition your company made that codes in a different language and uses different methodologies to you, how you can cope with that. Okay, so EDA vendors are supposed to supply solutions to problems like that, because there is no language reference manual that tells you here's how you connect system Verilog and VHDL, or here's how you connect system Verilog to assertions to VHDL. This is the thing that the EDA Talks company does. So the languages are defined in IEEE standards called Language Reference Manuals. Things like this, where you're interfacing between two languages and you'd like to things just to hold together nicely. This is what EDA vendors do, provide a solution. So hopefully you found that useful. And so what I'll do now is just show you, if you're interested in this kind of thing, where you can get training courses from Cadence. I hope you found this video useful. If you're interested in these kind of topics, you might be interested in the training courses. So if you go to cadence.com/training, choose your region, you can see a list of courses which are available in the various tools and languages also. So we're talking about functional verification. So if you expand this, you'll see all the formal courses, language courses. Some courses are also online, so you don't need to go to a classroom or have someone come to your site. You can follow the course at your own pace online. That's known as ILS, Internet Learning Series, so you can do that way of learning if you wish. Okay, so thanks for your time, and thanks for listening, and goodbye.